All right, the BSc in physics from Santa Clara University, new MSc. Crew chief at Zong International went out and collected data, which is good to see that. Lots of experience with eyepiece, CSAMT, MT, gravity, downhole EM. Started MSc in 2021 and is now done.
Yep.
And today we are going to learn about differential equation magnetic inversions.
Thanks, Ross. All right. So this talk I'm giving is basically very similar to my thesis defense, which I just gave a few weeks ago. It's called the differential equation-based framework for magnetic inversions to address challenges with high susceptibility and remanence. And the research was done at the Geophysical Inversion Facility at UBC, and it utilized the SimPEG open source framework. So the main goals for my research were, one, to develop a comprehensive framework for magnetic inversions, also to improve geophysical inversion strategies to better recover highly susceptible targets and magnetic vector models, so MVI models, and then 3, to enable large-scale inversions for magnetics in general. Okay, so a motivating data set is the Osborne deposit located in Queensland, Australia. And initial drilling at the deposit missed the target, and that's because they neglected self-demagnetization, and I'll talk about this more later. Okay, so another motivation is just the huge amount of large magnetic data sets, high-quality data sets that are available. And for inverting a lot of these very high-quality, huge data sets, it can be infeasible. And for big problems, even if you can do it, it can often be expensive for folks. So, all right. So for an overview of the talk, I'm going to go through the background of magnetics first, probably a lot of stuff that people here know about. I'm going to talk about the forward modeling and inversion framework that I've developed within SimPEG. And then as subsets of that, I'm going to talk about magnetic vector inversion and then inversion to account for high susceptibility. And then finally end with those a few case studies. Okay. So magnetic data provides information about the magnetization of the subsurface. And generally, most classically, we've assumed that this magnetization is in the direction of and proportional to the background geomagnetic field, which you can see there. But if there's remnant magnetization or self-demagnetization, then these can change the direction of magnetization. And because of that, you can see that the external field is also changing. So we need to be able to model these factors. Okay, so to model in terms of the magnetization, we can use Maxwell's equations in the differential form. The first of these being that the divergence of the magnetic field is 0. So all these field lines basically start and end on themselves. Then we have this magnetizing field, H. The curl of that is 0, so that allows us to define a scalar potential and use potential theory to solve all these problems. And then finally, we tie these two fields together through the magnetization, which is this quantity here, which is a vector field that's just internal to the body there. Okay. Yeah, so in order to do this, we need to say how H and M are related. And we do this with these relationships here. The first being that we use susceptibility to define how the magnetization occurs in response to the applied field, which is the ambient geomagnetic field and any secondary fields that are generated by the geology itself. And then also we use a vector field here notated MR, and that describes on the timescales that we're modeling here a permanent magnetization. So just talking about some various ways that we could model this. This is the most classic one that people have often done, which is assuming a low susceptibility, about 0.1 SI or less. We assume that the magnetization is in the direction of and proportional to the Earth's field, like I talked about. But oftentimes, if the susceptibility is very strong, then there's this self-demagnetizing field that comes into account here too. And this is that second term here. And so if you have very high susceptibility, this tends to oppose when not accounting for it, which is why it's called self-demagnetization. But it can also, you can see it's not directly opposing it, so it can also alter the direction of magnetization and therefore change the shape of those anomalies. A more general solution that we can use here is accounting for both high susceptibility and remanence, and that's the code that I've done here. And then finally, what we can do is just forget any how susceptibility or remanence goes into the total magnetization and just invert for the total magnetization. And that's called MVI, what people are often doing. The downside of this is then you don't know whether it was susceptibility or remanence that caused that, basically. Okay, so current approaches, oftentimes integral formulations are used for the linear problems, which is MVI, or the low susceptibility approximation. These are good for modeling linear physics, basically where we can form this sensitivity matrix here and then multiply it by a vector that has all our magnetizations. The downsides of this is generally you need to form and store G for inversions, and this can make it not feasible for very large scale inversions. Also, we're not able to account for non-linear effects or self-demagnetization. Another thing that has been developed is a differential method for high susceptibility. So this is, you can't really see it there, but this is modeling that self-demagnetization effect. There's challenges with inversion approaches to this, so we're going to talk a bit about some strategies for that. And then finally, we can't model remanence or do magnetic vector inversion with this. Okay, so I talked about the most general formulation here, which is accounting for self-demagnetization and remanence. So what we can do is we can take this relationship, and here you'll see that I'm using the magnetic permeability and susceptibility. Basically, just I'm talking about these interchangeably. They're just the same physical property. And so we combine that with Maxwell's equations, and then this is the PDE that comes out that we need to solve. Okay. So in order to do this, we use the finite volume method. And in this, basically, we have all these control volumes. So we discretize the subsurface with a bunch of cells, all these control volumes, and then the flux of the magnetic field. So the field times the area that's leaving one cell is equal to that's entering another cell. Okay. So the main points for this, going over it quickly, is just conservation laws, like I just talked about, talking about the continuity of the magnetic field. This particular version that we have in SimPEG is also mimetic. So that means the discrete operator and the discrete magnetic field, they mimic qualities of the true operator. And then finally, we use the weak form here, and this allows us to put these variables, which are at the cell centers, onto faces. Okay. So jumping over this real quick, this is the discrete form once we work through all the math there. And then we have the magnetic field B, and this is the magnetic scalar potential that we want to solve for. And so this is the total discrete PDE. Okay, so basically when you do all the math and write it out like this, it gets put in this matrix vector format. So we have this matrix A, a vector of the scalar potentials, and then the right-hand side there. Okay, so we need to invert that matrix basically, and then we solve for the potential. We take that potential and we can plug it back in, and then it's our data. Okay, so I've also developed a secondary formulation here where we break the potential into a primary potential and a secondary potential. And one of the upsides of doing this is we just have a zero Dirichlet boundary condition. So we can use an octree mesh, which we have in SimPEG, and pad out very far to satisfy that boundary condition there. Okay, but we need to know basically that we're doing the right thing. So the only analytic solution is for ellipsoids with uniform physical properties. So I took that analytic solution and I tested against it, and you can see here's a kind of a rough discretization, but you can see that they're aligning fairly well. And then also for ellipsoids, if the physical properties are uniform, then the average internal field is also uniform. So I compared those quantities for the analytic solution and for the numeric there. And you can see that the solutions are aligned really nicely. Okay. So now that we have a forward modeling that we can trust, we need to be able to recover the subsurface body from the data. And if we could measure this data everywhere like this, then we could probably recover that perfectly. But in reality, we have only a limited area where we're measuring this data, right? So then we need to insert prior information through this regularization term in order to recover something that resembles that. So one thing that can happen in potential fields is if you just left everything in this form, you could recover a model that is just right across the surface. And that's because potential fields basically have no depth information. So we can use depth or sensitivity weights, and that'll get rid of that issue. We can also have something that you've probably seen where we have these overly smooth models. And so we can use this choice of norm there, and a lower choice of norm will tend to compact the result, so we don't have those issues either. Okay. So now talking about magnetic vector modeling as a specific subset of the differential method. Remember, that's where we're just modeling the total magnetization, which is accounting for the induced and remnant, but we're just modeling this guy here, so we don't know which is which once we recover that model, basically. So once you run through the math there, you can do a similar thing, and this is the form of the PDE that we need to solve. Okay. So the important thing with this here is I mentioned that we invert this matrix basically, or we solve this matrix vector system. In this case, the matrix isn't dependent on the model. You can see the permeability there is the permeability of free space. And because of that, we can factorize this once, which is the expensive part, and just store that factorization. So that's going to be important for large scale modeling. So one thing is how accurate is our method, because the integral method that's commonly used is exact for these cuboid cells there. And basically what I'm showing here is the analytic solution versus the integral and the differential solution. And you can see that the big place where there's errors there is basically where the discretization of our smooth surface isn't accurate. So I'm comparing to this ellipsoid here. And so basically what that's showing is both these methods are accurate enough ways to solve for our fields there. Okay. So one big upside of the differential method is it can be a lot faster for large scale problems. So the integral method that's commonly used, it tends to be dependent on the size of our data vector, or sorry, our model vector times the number of data. And then even when we're computing the data, there's a big dense matrix G. And so that's fully dense. So that can be kind of expensive when you have to do it over and over and over again. For the differential method, it tends to be more dependent on the total number of cells. And then when we're computing our data, you can think of it as doing a similar thing to this, except we're breaking it up into parts where all of these matrices are sparse. And because of that, we're doing way less computations, and it can start to be a lot more efficient. So what I did here is I compared the differential method with a fairly fast integral method that's implemented in SimPEG using this open source package Choclo and Numba from Santi, and it's parallelized and comparable to Fortran or other compiled languages. And then I compare these as a function of M, where M is the total number of model parameters. And I'm increasing the size of the problem here as I'm comparing these, basically so where the data are increasing proportionally and the total number of cells are also increasing proportionally. So one of the major things is the storage. And you can see here for storing just the sensitivity matrix for the integral method, that starts to explode fairly quickly as the problem size gets pretty big. For the differential, we don't need to store that. We have these sparse matrices. So you can see that we have a lot of savings as the problem size gets really big. I don't have a fourth point up here for the integral because with the 1 terabyte cluster at UBC, I wasn't able to do that one. Okay, so for an initial forward modeling, basically the limiting steps there are the formation of G, or the factorization of that matrix like I talked about. And you can see that the integral method is tending to scale quadratically, which is kind of what we expect because the number of data points are increasing in proportion to the size of our mesh. Whereas the differential is not so dependent on that. And you can see that here we're better than quadratic, which is nice. Okay. So, and then I'm talking about an additional forward modeling. And the reason for that is we know in inversion, we have to run these forward modelings over and over again. So for the integral, the limiting case there is the dense matrix vector product. For the differential, it's that sparse matrix vector product. So you can see that as our problem size gets bigger, once again, the differential starts to significantly outperform the integral. And then finally, I ran inversions as I increased the problem size. And you can see basically the exact same thing. And this is showing that the integral is most limited by those dense matrix vector products, while the differential, because of the sparse matrix vector products, we're able to do very big problems. Okay, so talking now about actually inverting MVI data. So like I mentioned in the beginning, this can model remanence, self-demagnetization, all these factors. So the question is, why not always do it? Well, the reason is there's 3 parameters per cell. And for inversion now, we have additional non-uniqueness. So this means that we could require additional prior information. So for example, I have a susceptible only cube here. And I forward modeled data for this. And this is showing inversion results just for a susceptibility inversion and for an MVI inversion. And you can see that even for the L2, the susceptibility does a decent job of centering on that body, whereas the MVI is less well constrained. So it's way more smoothed out. Okay. So like I mentioned in the beginning, one thing that we can do here is use sparse norms to try to compact that body. When you use these sparse norms or IRI and Geosoft, basically, yeah, we're just trying to compact it. But when you do that with MVI, what you'll often see is you'll recover these coordinate aligned components if you do that naively. And that happens if you do the smoothness, which talks about how the model is changing at the boundary, and the smallness, which is the model components in general. Okay, so these authors of this paper, they decided to regularize the amplitude, leave the model in Cartesian, but regularize the amplitude. And you can see that the results I did a similar test to what I showed. The results are better, but you can still see these artifacts at the boundary where you have these coordinate aligned components. So what I did was I implemented this, where now we're using I implemented this, where now we're using a smoothness term, where we're taking the amplitude of the gradient of the X component and the Y component and the Z component. So when you do it this way, there's no artifacts related to the coordinate system that you choose, which is nice. So you can see that their method is fairly good. We're recovering a magnetization that's in the direction of the Earth's field with that low susceptibility approximation. But yeah, this new way of doing the smoothness term also improves it even more. Okay. Now changing topics a little bit. Now I'm going to talk about using the code to account for high susceptibility, which is the self-demagnetization effect with that self-demagnetizing field that I talked about earlier. This is the partial differential equation that we're solving in this case. There's 2 big things with self-demagnetization. One is the saturation effect. You could see when we're neglecting self-demagnetization, the magnetization the ratio of that with respect to the applied field is basically uniform. And then when we account for self-demagnetization, you can see that as we're increasing the susceptibility, the magnetization is not increasing proportionally. Another thing is rotation. If you're not accounting for self-demagnetization, you're always assuming that the magnetization is in the direction of the Earth's field. But when you do account for it, you can see that it's rotating towards the longer axis of that body there. So what I'm showing here is this is low susceptibility. This is all accounting for self-demagnetization, but this is showing at low susceptibility that it's a good approximation. We're seeing that it's all in that same direction. And then at high susceptibility, you can see that that approximation breaks down, especially as the body is elongated there. Okay. So going back to that initial motivating example, that's a synthetic, this is a synthetic plate model that's inspired by the Osborne deposit. And the initial scenario there was they didn't account for self-demagnetization, and they interpreted these ironstones to have a dip of something like this, when in reality, when they did account for self-demagnetization with their modeling, they were able to forward model the true dip, which helped with later drilling. Okay. So here's the model I generated, and here's when neglecting self-demagnetization, you can see the magnetization is very high and all in the direction of the Earth's field. And then when you account for self-demagnetization, the magnetization is actually way lower. And then it's also rotated and not evenly rotated. You can see near the edges of these plates that it is different from the other edges. So it's a kind of complex thing to model in actuality. Okay, so this is showing just a profile above those plates. And this is showing the saturation effect, so not accounting for self-demagnetization. And then when you start to account for it in the modeling there. And then I also took this magnetization and plugged it into MVI and forward modeled that just to show that we are also capable of modeling that with MVI. And then the other thing is, even if we normalize these, we still have that rotation effect. So that's changing the actual characteristic of the anomaly. And because of that, we're not only going to underestimate our susceptibility, but you can actually misplace it. Okay. So I first ran smooth inversions for all of these methods, first using the low susceptibility code. And you can see that just like the example from Clark here, we recovered a more vertical dip. When we did the MVI, it was way more smoothed out, like we mentioned before, and it doesn't really represent the body very well. But interestingly, now when we're accounting for self-demagnetization, it's improved just slightly, but you can see the susceptibility that we recovered is not all that high, actually. So we're not really simulating those self-demagnetization effects. Okay. So then using sparse norms, now, once again, when not accounting for susceptibility with the standard code, once again, we're recovering a dip that's more in the vertical. With MVI, interestingly, because we don't have any constraints on what the direction of that magnetization should be, it's also recovering a model that's similar to the low susceptibility. And that's just indicating that MVI is less well constrained here. And we need more information if we want to use it for this type of problem. And then finally, for the high susceptibility sparse inversion, you can see that it is able to recover the dip there. One thing is, because of that saturation effect, I needed to use bound constraints for the high susceptibility model. So just showing a few different bound constraints here. In all cases, it was better at recovering the dip, but as we got closer to the true susceptibility of that body, which was 6 SI, we started to do better here. Okay. So now looking at something that's a little more extreme, and I want to talk about some of the limitations of that method that I just showed you. So I forward modeled data for a plate with kind of extreme geometry and very high susceptibility. And this is just showing the magnetization of that plate near the surface. And you can see that the magnetization is all shifted towards the northern part of that. So what we see then when we run the inversion is, here's our smooth inversion, and it doesn't do a very good job of placing the body. And then even when we do the sparse inversion in this case, it does a poor job. So the idea here was to do a hybrid-parametric sparse inversion instead then. And the idea is to fit a parametric model and then use that as a reference model. And these authors implemented that strategy for EM, and I'm applying it here to MAG. But then a few things that I've changed from their methodology is I used the sparse norm inversion for the voxel portion of the inversion. And then also I'm using PyTorch, which is a machine learning library in Python, basically to compute these derivatives. And that means that although I'm just using an ellipsoid here, you could use basically anything that you can program up. Okay. So the results here, you can see that this is the initial model, and then here's the final parametric and hybrid. You can see that from this angle, the parametric and hybrid look the same from the sections, but from the depth sizes, you can see that the parametric does a decent job of recovering the dip and is over that body. But then when we do the fully voxel-based sparse inversion, it helps to refine near the edges there. Okay. Okay. So finally, I'm going to talk about what I just showed you, and basically first talk about running some MVI for a very large scale inversion, and then using the hybrid parametric inversion at the Osborne deposit. Okay, so the study area, this is an open data set from Geoscience Australia in Mount Isa Inlier in Queensland. And there's a huge amount of data there. And once I downsampled this, I had 240,000 data points. So it's quite a bit of data. The mesh was a total of 18.3 million total cells with 13.7 million cells below the topography. And this meant that we had to invert for 41.1 million model parameters. And for the computation available, I had the cluster at UBC with a terabyte of RAM. And we used the Paradiso solver to invert that big linear system. Okay. So first I tried to do this inversion with the integral method. The hypothetical storage of that sensitivity matrix alone was 39 terabytes. So that's way above my 1 terabyte limit. Not able to run that inversion. For the differential method, there is a significant amount of storage because I'm storing that factorization, but it's quite a bit less. So it's 211 gigabytes. The initial factorization took about 12 minutes. Each additional forward modeling, once I did that factorization, was about 20 seconds. And then each inversion iteration was about 25 minutes. So I was able to run the full inversion in under 2 hours. And then I was able to do a forward modeling with a single forward modeling with the integral because we don't need to store the sensitivity matrix there. And you can see the time for the single forward modeling and the data that if this value was 1, we'd be fitting the data perfectly. So both of these fit underneath our data tolerance there. Okay, and this is just showing a slice of the inversion model 400 meters below the mean topography there. Okay, and so if you look at the, down in the bottom here, that's the Osborne deposit for scale. And this is that ironstone deposit that I mentioned before. Initially, there was 20 to 40 meters of cover there, but there's a big magnetic anomaly, so that sparked some interest. But the initial magnetic modeling, because it didn't account for self-demagnetization, those initial drill holes missed the target. Okay, so the idea was to run the hybrid parametric inversion, like I mentioned. So the first stage of this, I fit these ellipsoids by eye, and here you can see the true data and the predicted data once I did that. So I just wanted to get them in a decent starting point. This is the final parametric. So now you can see that the predicted data is pretty close to the true data. And then this is the final hybrid where now we're fitting the data very closely. And you can see that our model has actually, the hybrid has actually changed our model quite a bit also. Okay. And then this is just showing a slice from that, from a case study that was done there. And so this is that initial parametric. Now you can see the final parametric model. We're able to recover the dip of both that was labeled the magnetized ironstone and the barren ironstone over to the right here. And then finally, when we run the voxel-based inversion, we're able to recover this mineralization that's associated with the westernmost ironstone also. Okay. Yeah, so in conclusion, what I've developed is a general framework to model self-demagnetization or remanence or both simultaneously within SimPEG. Modularity within SimPEG allows for incorporation of various types of prior information. And this code allows for very large scale inversions in a short period of time. All right, some future research topics are modeling both remanence and susceptibility. And I didn't look at that for this master's, but that's a real challenging thing because then we're trying to account for all these factors. But looking at maybe if we have downhole samples or what do we need to actually separate those two. Looking at using joint inversion potentially to do that. I want to look at different types of data sets, including modeling gradiometry and looking at what we need to do to model downhole magnetic data, and then maybe thinking about probabilistic inversion and machine learned regularization also, future topics. Thank you.
Lots of time for questions. I've got a comment to start with and then a question later. You just got a master's out of this?
Yeah.
Seems like a PhD work to me. I've been out of academia for a while. Boy, this is a phenomenal amount of work.
Appreciate it.
Yeah.
No, that's 100% not. Yeah.
It's Lindsay's fault this time.
Yeah, fair enough.
You just want to hang on to him for a while. He's going to stick around for a second. You're really milking this guy.
Always sets him up for a fabulous PhD.
Yeah, I'll say.
So I did read the bio correctly.
Yeah, it's true. It's true. Well on his way.
My question, excuse the ignorance, but I don't know what's happening physically at a mineralogical level of what the self-demagnetization is. I don't really understand that at all.
On mineral. Okay.
Can you explain what's going on right down at the magnetite or whatever magnetic mineral you're talking about? What's going on?
To be honest with you, I in doing all this research, I think of susceptibility as a bulk physical property. And then thinking of, okay, when basically you can think of it as basically there's like, when we're modeling it in bulk, you have some kind of buildup of magnetic charge. That's not here. Let me jump back to.
Is it the difference between the surface of the mineral versus the material of the mineral?
Yeah, so you can see here that where our magnetization, however you have this magnetization where there's a divergence of that. So at the boundary, you can think of there as a buildup of surface charge. And when that surface charge gets very high, then it generates a backfield.
Oh, okay.
And that's at a macroscopic level that we're actually modeling this. So,
but it's probably happening at a microscopic level.
Yeah.
Is that right?
I mean, I think at the macroscopic way is a gross way of modeling all the microscopic stuff coming together at once, basically.
Right.
Break it up into its like individual magnetic things.
Yeah.
It's all news to me. I used to just teach susceptibility and remanence, and that was it. Huh.
Yeah, generally 0.1 SI self-demagnetization isn't very much of a big deal, but if you start to push it up very high, right, that's when you see it. So iron deposits, those ironstones, yeah.
But if you imagined a little chunk of material here and it's got a susceptibility that's associated with it, right? And now, if you have a magnetic field that's coming in on here, and then you get a certain magnetic moment that's attached to it. But if you had surrounding material around here that's also getting magnetized, and that's going to affect what the magnetic field is that's impinging on it. So it's just that the magnetic field that's actually coming into this little cube that you're thinking about, it's just different than what you had thought it was going to be, because it's that initial field, but then it's got all the stuff from elsewhere. So hence that tends to reduce the resultant magnetic field, and hence it tends to be called self-demagnetization.
And depending on geometry, you can also rotate it.
Yeah.
Or worst case, if it's in line with the field, then it's going to completely oppose to it. It's going to reduce the total magnetization. So the geometry is important for sure. He showed up with the oval. Yeah. No.
Right. Yeah.
Yeah, so when that magnetization rotates, that's where the characteristic of that anomaly is actually changing. Because if it's not rotating, you can think that it's just pointing directly back against it, and then it's just decreasing the anomaly that you see. But when it rotates it, that's when if you don't account for it, it'll start to shift your result from what it should be.
You quoted a few papers in this. How long has this been, of concern to people doing this sort of work? Has this been going on for quite a while? Or?
This paper here is from 2000, from a geophysicist in Australia, David Clark. His papers I based a lot of my work on. He's really great potential field geophysicist.
So back in the 80s, this wasn't known at all.
I don't know if that's the case.
I think it probably was. I think it's been around for a very long time. It's just that there's not very many places where you have such really high susceptibility, so it's not such a big deal. Pete Fulliger, I think, did a fair bit of work at self-demagnetization too.
He has some codes for sure.
It's Peter here. Can you hear me?
Hi, Peter. Yeah, go ahead.
Yeah, I worked on the Osborne deposit when it was discovered. And I remember that, the geologist looked at the mag profiles and he missed everything, and then we went in to look at it, and we realized that demagnetization was important, and it changed the dip of the bodies when we considered it. And then we drilled it and were successful. But modeling it's been a challenge, since we found the deposit. And I'm really impressed by these results because I think they do a really good job of allowing you to replicate the data, and which is what you're trying to do. And it's very nicely backed by theory, which is always good too. So I mean, I've seen the MVI models done, and sometimes they have fit, but it's always made me a little uncomfortable. And actually, knowing that the rotation of the magnetization dips in the deposit came from the demagnetization, seeing it accounted for properly and seeing it fitting and being able to invert, I think is a great achievement. So I'm really impressed.
Yeah, I think I was looking at some works that modeled it with MVI too, which you could model it with MVI. But like I talked about, there's an additional degree of non-uniqueness there because you don't actually know the magnetization direction. And then when you're modeling it in terms of susceptibility, you're basically computing the magnetization direction from the susceptibility. So, yeah.
We actually built a borehole magnetometer to help us work there. And so there is borehole data, but where it is now, I have no idea.
Oh, that'd be great to look at. That'd be super interesting.
Thank you, Peter. Richard, did you want to ask your questions yourself? I can ask it for you. That's okay. I'll ask him. Can you describe? I'll ask Richard's question. I guess I'll move over. You can see it yourself. So can you remind us what's the kind of like the workflow for the parametric inversion? So you're going between a parametric and then a full.
Yeah, the workflow was first to fit those parametric bodies and then use them basically as a reference model.
So you see the inside the voxel inversion after.
Yeah. So basically, what I was showing here was, so this is my initial the workflow was I did a rough fit by eye with the initial parametric, and you can see that it's not aligning really well right there. And then this is the final parametric where we start to recover the broad features. And in this slice, the hybrid voxel also helped us recover this extension of the more magnetic body there. So that was the workflow from one step to the next.
And then the voxel was using a sparse constraint on it, so they're closer together.
Yeah, because using just the smooth, it just kind of smooths everything out. Right. It's like, that's not what you want when you're doing the parametric to start with. So.
Sure. So thank you. Anyone else?
It's Peter here again. I just might comment that we did our forward modeling using parametric models, but we used triangular facet models, and we actually checked them against ellipsoids, and then calculating the charges on each triangular facet we were able to introduce an iterative procedure to get the demagnetization. So we did the forward model, and we had the charge on every triangle, and then we recalculated the internal fields using the charges on every triangle, and we continued to do that until we had an estimate of demagnetization. And that actually worked really well, but it was very much a forward model. So, I guess you could you could do an inversion of the parameters. And I know people have done that, not for magnetization, but for salt domes. But we didn't do that. We just beat ourselves up doing forward models.
Peter, a question for you. What's the, sorry, I'll take over. What, do you know the geometry at the bottom of Osborne? What does it look down dip? It just keeps going?
No, I'm sorry, I don't. I probably could find out, but I don't know it in my head.
Because that's the only thing already said. Always that cross section, and we don't really see what's beyond, but that's good.
Yeah, there are some other
sections.
Yeah, they have some 3D plate models actually. Geoscience analysts, I didn't put it in here, but yeah, they continue quite
mostly straight, or
yeah, mostly straight.
Okay.
They really are like sheet-like bodies. So.
Okay. I guess Mag just doesn't have the signal at that point to be able to model it.
Yeah, with parametric, you're doing a good job at fitting the top. And
yeah.
It's kind of continuing it, but yeah.
What else? Online? Don't be shy.
Oh, I've got a question. You said you talked about the difference between the integral and the differential methods, and how the differential methods sort of take over being advantageous for inverting large models. I would say like most realistic data, would take up a lot of required lots of modeling, lots of cells.
Yeah,
they require a large model. Is this differential method restricted to this potential field method, or can be extended to other physics?
It can be extended. It is in SimPEG. It's extended to other physics. There's some stuff. Part of the reason why this is so fast is because I only need to factorize that matrix like I talked about. I only need to do that one time for this. And a lot of EM problems and whatnot with this coefficient matrix will be changing every iteration. And so you keep needing to refactorize over and over again. From my understanding, I haven't done a lot of EM, but that's the slowest part of that.
Okay.
So I'm able to do this factorization once here and just store it.
Okay.
And that's part of the big speed up for the method for using it for
Mag. Okay, yeah. But for EM, you'd have to do that.
Yeah, factorize it over and over.
But still, if you're using sparse matrices, and
yeah,
it would still be a speed up for EM using differential approach.
I assume, yeah, it would be compared to some other methods. I mean, that's how it's implemented in SimPEG, right?
Yeah, we
method
use
of choice.
Differential equations for all the EM simulations. Inversions.
Was there ever integral forms for EMs?
Well, no,
There.
I mean, we use propagator matrices and things like that for 1D codes, but yeah, we never really did much for integral equation methods. Yeah.
It's like basically you need to know what the current, the induced current or source current in all those cells or regions are, and then you have like a Green's function, but you need to keep what that is.
Solve it.
So then you have to solve that anyway.
The Utah group, Stanoff, they did a lot of integral equation techniques. We never picked that up.
What's the takeover? What's the cross point in your plots in time, not in memory? But what was the
sorry, where they
was the crossover? Yeah. You're reading my caption?
Yeah. I thought you were reading someone else's question.
No.
I was like trying to read it for myself. Yeah, it depended on where. Like for the storage, the differential was always significantly better.
And yeah, no, for the runtime, yeah.
Yeah, for forming G or storing G, the differential. I mean, even for pretty small problems, still. I guess the big one that people probably care about is inversion. And here, yeah, I guess 10 to the 6 around.
Million cell. And you were solving like because the CGs, like you're doing the same number of
yeah.
CGs.
Yeah, that's correct. Yeah.
That's perfect. Great.
Yeah, I think that was the big speed up was the CG iterate just over and up that 4 model over and over.
Yeah, that's where your cost is too,
yeah.
Right? Mm-hmm. Did you have to cap it? Did you?
I didn't have to. I just did for this, so that yeah, I just did it.
Yeah, you did it to be able to compare. But...
Yeah.
And then for your weighting, you just approximate the sensitivities.
Yeah.
Like 1 over RQ or whatever.
Yeah, depth. Use depth.
Yeah, sure.
But distance weighting too.
Yeah.
Yeah.
Makes sense. Yeah. Last call for questions. Okay, good. All right, thank you again.
Well, there's no